Hi all, welcome back to the Martin Lab. This is going to be part 2 of our anthocyanin adventure. So in the last video you saw our very red hibiscus change to sort of bluish purple in front of your eyes. In this video we'll explain why that happened and the chemistry behind it.
In part 1, you learned that the color of an object depends on the wavelengths of visible light it absorbs. You also learned that anthocyanins are plant pigments that absorb visible light and give some plants their reds, blues, and purples. You then saw red hibiscus anthocyanins turn purple on printer paper in a matter of seconds. In this video, we'll explain the chemistry behind the color change and how you can use it to make some pretty neat paints. It turns out that anthocyanins are what you might call pH sensitive. They respond easily to changes in pH. If you've ever had hibiscus tea, you'll know that this flower is very acidic, almost like a lemon. It has a low pH. Most printer paper, on the other hand, is buffered to be slightly basic, and it has a high pH. The high pH of the printer paper is enough to turn your red hibiscus anthocyanins purple. But what exactly is going on? To understand this, we must first understand something about the structure of anthocyanins. Anthocyanins all have the same basic structure. They start with an anthocyanidin backbone, which can have varying combinations of hydroxyl, hydrogen, and methoxy groups surrounding the rings. The exact placement of these substitutions give rise to many different anthocyanidins, each of which can become the basis for many more anthocyanins. Anthocyanins are then formed from these anthocyanidin backbones by replacing the hydrogen on one or more hydroxyl groups with a sugar. Here, this hydrogen in cyanidin is replaced by glucose to make chrysanthemin. Many different anthocyanins can be derived from the same anthocyanidin backbone by varying the type and location of sugar substitutions. In addition, they may produce slightly varied ranges of colors depending on the details of their molecular structures. Individual plants can have a complex mixture of anthocyanins, each generated by enzymes adapted to catalyze reactions like the sugar substitutions that turn anthocyanidins into anthocyanins. But what does this structure have to do with pH? If you take a closer look at chrysanthemin, you'll notice that many of the variable R groups in the anthocyanidin backbone are hydroxyls. These OH groups are very good at losing protons with an increase in pH. With every lost proton, the overall molecule gains a negative charge, and for anthocyanins, this change is related to its color. The structure for chrysanthemin that we were looking at before is its structure at pH less than 3. You'll notice a positive charge at this low pH. Generally, anthocyanins are red at low pH, purple around neutral pH, and blue at high pH. In even more basic environments, some anthocyanins turn green or yellow. When your protonated hibiscus anthocyanins came into contact with the basic printer paper, they quickly began losing protons and changing color. Because of this immediate and reversible property, anthocyanins are often used as universal pH indicators. But today you'll be using them to make some nice watercolors. In today's activity, you'll be using household acids and bases to change the colors of your anthocyanin paints. First, set up your palette. For each column of 3 wells, fill 1 well with nothing, 1 with vinegar, and 1 with baking soda. This will set up your control, or the rough flower pH, your acidic, and your basic environments respectively. Now that our experiment's set up, we can pour our paints into each environment. Pause the video here if you'd like to guess our paint's new colors and which wavelengths of light they absorb under each condition. We'll start with butterfly pea flower in the acidic environment. Butterfly pea flower is normally a deep blue, but when it touches the vinegar, it immediately turns a pink purple. In baking soda, it turns a light cyan. Now do the same with hibiscus. Will you get the same results? Notice that in vinegar, the color doesn't change. Why do you think that is? Note also the strong reaction hibiscus has with baking soda. Soon after, it turns a dark purple. These are the colors you'll have available for your final anthocyanin painting. But remember to test them out on your worksheet before use because basic printer paper may change the color. Before we show you our works of art, we again wanted to put our results to the test. So we used a pH meter and a spectrophotometer to visualize how anthocyanin color changes with pH and visible light absorbance. Here is the color wheel for reference. Remember that if an object primarily absorbs one color, it will appear as the complementary color on the color wheel. Our absorbance spectra show this to be true. While these butterfly pea flower anthocyanins are still blue, they primarily absorb around 530 nanometers, or the color orange. This is at a pH slightly below neutral, but at low pH, the spectrum shifts. The new highest peak is around 575 nanometers, which is well into the yellow part of the color wheel, meaning that we mostly see purple. In this demonstration, we've added vinegar to bring down the pH. Because this is a reversible reaction, we decided to perform the same experiment but in the opposite direction. We added baking soda directly to the now highly acidic solution, producing a beautiful blue-green volcano. The resulting spectrum showed a slight shift toward longer wavelengths, though nothing dramatic. Still, the absorbance of wavelengths near 640 nanometers likely contributed to the green-teal colored froth in the video. Here's my lab mate's comment on the situation.
Science volcano.
While the color of butterfly pea flower varied most with a decrease in pH, hibiscus was the opposite. This is because hibiscus is naturally very acidic, while butterfly pea flower is closer to neutral. You'll notice here that the peaks of the spectra taken at both control pH and low pH hovered around 520 nanometers, or green on the color wheel, which means in both cases these anthocyanins were perceived red. Again, we then added baking soda to this low pH solution, which resulted in an immediate color change. The spectrum at this new high pH had a peak at roughly 590 nanometers, or yellow on the color wheel. These anthocyanins were then a deep purple. In these experiments, we were limited by both the strength of baking soda as a base, and also the fact that we dumped all of it into very acidic solutions. With much higher pH, it's likely that both hibiscus and butterfly pea flower anthocyanins would undergo even more changes. And that's it. You now know the secrets of anthocyanins and how they respond to changes in pH with changes in visible light absorbance. We hope you've enjoyed these videos, and please feel free to contact us at martinlabuci@gmail.com or check out our other research at probemonkey.com. Thanks.